Hello, everybody. I thought that I would make a little lecture here about one of my favorite toy quantum field theories for illustrating properties of things like parton densities and so forth. So today my plan is to go through the steps for renormalizing this theory and showing you how you get the beta function, the running of the coupling. So start by just explaining what the theory is. So it's going to be the Yukawa field theory, and it's actually specifically scalar as opposed to pseudoscalar Yukawa theory. And we're going to have multiple fermion masses, multiple masses in the problem. So every particle is going to have a mass. Okay, so multi-mass. And the idea is that this is going to be a stand-in for a kind of nuclear interaction. So the Lagrangian for the theory, I've written it right here. The Lagrangian density has all the elements you should expect to see. I've got actually two fermion fields here. One of them is labeled by psi, and one of them is labeled by a capital H. I have in mind that H is our stand-in for like a hadron field, and psi will be kind of like our stand-in for a quark field. And you can see that reflected in the way I've labeled the mass terms. So the quark field, psi bar psi, has a mass term m sub q for quark, and h bar h has a capital M. And then we've got the scalar field here, and its mass here, its mass term here, there's an s for a scalar. Okay, you could think of this as like a scalar gluon perhaps, or a pion maybe. Okay, again, this is a toy field theory. It doesn't exist in nature, but it's got many of the properties we like to discuss. Renormalizability. This is a renormalizable theory. And it kind of mimics many of the properties that we do want to have in a physical theory. It's got particles with spin, which is nice. I put scalar coup out here. That's an abbreviation for scalar coupling terms. So in addition to this kind of coupling, so this is what in the Feynman diagrams will give a coupling that looks like this. Okay, all three particles interacting at a point, plus the Hermitian conjugate term. And in addition, we have to have couplings like this, and then a quartet coupling like this, if we want the theory to be renormalizable. And I'm not going to deal with those interactions, so I'm not going to write them down here. I just want to remind you that they're there. Okay, so I've written this as the bare Lagrangian, so there are 0 subscripts on everything. The fields are all bare fields. This is the defining Lagrangian of the theory. And by the way, when we regularize the theory, because we're going to have ultraviolet divergences, I'm going to go to dimension equal to 4 minus 2 epsilon. And then we'll be taking the limit of epsilon going to 0. Okay, so just going through the steps we already did in our quantum field theory lectures and in class, we defined a bunch of new objects related to the bare objects by an overall normalization. So we're going to say the phi field, this field here, which is the scalar, gets an overall factor of z to the minus 1/2 times phi 0. Similarly for the two fermion fields. And that means that when we substitute phi, say right here, and h0 here, and psi 0 over here, we end up with just overall factors of z, s, zh, and zq for those terms. And of course, we have these subscripts so that they match with the particular field that we're looking at. Okay, if we do that substitution, then the mass terms get these overall factors of z, s, and zh, and zq. So keeping with the notation that we used in class, we just call that collection of factors here m sub s with a capital B squared. similarly for the fermion fields. The capital B here stands for basic. So if we do those substitutions, we end up with what I call the basic Lagrangian. It's the same Lagrangian, just with different notation. And it looks exactly like, say, the standard Lagrangian you would write down if you were not thinking about interactions or normalization. The only difference is that these kinetic terms have these overall factors, these overall normalizations, z sub q, z sub h, and z sub s. Okay, and again, the capital B stands for basic. That can be a little bit confusing because you might think B stands for bare. It doesn't in this case. Okay. Now, again, I hope these steps are familiar. We're just going through them to establish context for what we do next, establish notation and conventions and so forth. The next thing to do is split this Lagrangian into one with couplings and normalizations that correspond to the naive expectation you would have, just how you would start writing down Feynman diagrams, plus a counter term Lagrangian. So the way to do that is to just write each of these, first of all, write each of the z's as 1 plus a delta z. So these normalizations of the kinetic terms just become 1 plus delta z, each with the appropriate subscripts. The basic Lagrangian we can then split into something we'll just call MQ. This is the M that we'll work with when we're calculating Feynman graphs, plus a delta M. Same for the other masses. And then for lambda B, the coupling of the theory, this triple coupling right here, we'll write that as just a lambda without any subscripts or any other decorations times an arbitrary scale mu raised to the epsilon. So this is the minimal subtraction mu that we're ultimately going to want to use. And then plus a delta lambda to relate that back to the original basic lambda. Okay, so the next step is just to substitute all of these things in. And by the way, remember why we put the mu to the epsilon there. We want to have the lambda that we work with be dimensionless, because we know that once we remove the regulator, once we go to epsilon equal to 0, once we go to 4 dimensions, then we have a coupling that should be dimensionless. And that's what we actually want to work with in our manipulation. So we need to carry around this mu to the epsilon to make sure that the coupling here has the right dimension. Okay, so let's do that substitution, and we get to the final form of this Lagrangian that we're going to work with. There's the part that we use, that we start out with when we're writing down Feynman diagrams. And then there's the part that has counter terms that we have to add. So now there's a kinetic term for the quark fermion field with an overall delta z. And similarly for the other kinetic terms, there's a delta lambda for the coupling. Okay, and if we repeat all the steps that we're hopefully familiar with, you get a set of Feynman graphs. Well, before we get there, let's specify what kind of renormalization scheme we're going to use. So we're in the dimensional regularization regulation scheme. But now we have to say what prescription are we going to use to define all these delta parameters in this counter term Lagrangian? And therefore, what are we going to be, by extension, defining as the definition for all the parameters in the Lagrangian? Well, we're going to use standard from quantum chromodynamics, which is modified minimal subtraction. Remember from the QFT lectures what minimal subtraction was. Minimal subtraction said just subtract. The minimal subtraction scheme says just subtract whatever is multiplying the 1 over epsilon poles as you go to epsilon equal to 0, up to whatever mass terms you need in order to make sure consistent mass dimensions are there. Okay, now we're going to use actually modified minimal subtraction, which is barely different from minimal subtraction. All it means is that instead of just subtracting the 1 over epsilon poles, we're going to subtract the 1 over epsilon poles times this factor, which removes a bunch of constant terms order by order in perturbation theory that make the convergence a little bit better. Okay, so multiply the 1 over epsilon poles with that. Okay, and we talked a lot about minimal subtraction, and we compared many of the renormalization schemes back when we were having our QFT lectures, and we found a number of nice properties for the minimal subtraction scheme, especially in theories like quantum chromodynamics, where we want to be able to talk about the short distance dynamics independently of whatever mass scales might appear over large distances. Okay. So then we end up with a set of Feynman rules, and we're going to start using the Feynman rules here in just a moment. Maybe I'll draw a line down the middle of this page to separate the regular Feynman rules here on the left from the counterterm rules over here on the right. And I hope none of this is surprising or mysterious after you've taken the QFT class. Okay, remember we've got mu to the epsilon that I'm writing here explicitly if we're doing these Feynman rules in 4 minus 2 epsilon dimensions, space-time dimensions. Okay, that means that the delta lambda that I defined over here also has to have units of mu of a mass to the epsilon. Okay, if we're away from epsilon equal to 0. Okay, and of course we do have to remember that there are terms like there are Feynman rules for that kind of coupling and for this kind of coupling, but since we're not going to encounter them in the calculation I'm about to do, I thought I'd refrain from writing them down explicitly. Okay, so our task for today, what I want to go through today is how do you get the running of the coupling in this theory? So lambda here, this lambda that we have right here, is going to acquire some dependence on the specific scheme that we have, the specific renormalization scheme defined by the value, which is defined by the value of the mu that sits right here. Okay, and the dependence of lambda on mu basically tells us the dependence of the coupling on the scales that we're including in our theory. And that's the beta function. So we'll get to the beta function. And to get there, we have another number of things we need to calculate. We have basically the endpoint functions that you get in the theory. We have to calculate, say, the 2-point functions. Those all, when added to the counterterm contributions, tell us what the counterterms for the self-energy have to be. And then we also have to look at what kind of counterterms we have to add to the 3-point functions to make that finite. Essentially, we have to figure out what sort of 1 over epsilon poles are sitting here. Okay, that will tell us how these parameters of the theory run. Now, we've already gone through, at least to some extent in previous lectures, how to calculate the wave function renormalization factors here. And so I'm not going to repeat that here, but we're going to have to use them in just a bit. So I'm going to write them down here for you. And, I urge you to check if you don't remember how to get these, repeat the calculation of these graphs to figure out what these are. And shouldn't be surprising what they look like. The overall factor here might, the details of whether it's 1 over 32 or 1 over 8, you might have to check, but this should involve S epsilon over epsilon, and it should involve lambda squared. So what I'm going to focus on are these vertex graphs here. That's the last one that we have to look at if we want to get the beta function. And okay, actually we did do a similar calculation in the QFT lectures, but we looked at the phi cube theory. Okay, you look back at that, you see that we got the running of that theory. So this is a little bit different just in that it involves fermions. Okay, and I think that the best way to do this is not to just look at the the 3-point function by itself. I think it's more instructive to actually imagine that you're doing that 3-point calculation as part of some kind of cross-section calculation. So let's do that. So let's imagine we're living in a universe where this theory is an actual physical theory, and we want to calculate the cross-section for a quark, what I'm calling a quark here, and one of these scalar particles, pion or scalar gluon, whatever you want to call it, that they come in and scatter together, and they're going to fuse into a hadron, and a very far off shell hadron if we scatter them at very high energies. And that's eventually going to have to decay into some very high mass pair of a quark and a scalar in the final state. Okay. So physicists living in a universe where this is a theory might want to do this kind of calculation. Of course, there are many more diagrams like this, and they're the zeroth order diagrams that I haven't already written down here, because I take it for granted that you can calculate those contributions. But this is one of the calculations that you would have to do, one of the graphs you'd have to calculate. And let's make an abbreviation. Let me call this little q squared, to match with the kind of notation that we tend to use in QCD type calculations. Let me call that capital Q squared. And of course, little q is just, well, in the limit that we can neglect masses, it would be p plus little q, all of that squared, which would be 2p dot q. So really I should probably put, plus masses here, because there are mass squared terms there, but those aren't going to affect our calculation of the counter term, because that only has to do with the ultraviolet behavior of this loop right here. So it won't really matter what these masses are exactly. Okay, so what exactly do we have to calculate? Well, we have to calculate that graph from the previous page. And I'm just going to organize things a little bit differently here. I'm going to say, let's take that graph from the previous page. And actually, whatever appears here is not really of interest to us. It's this loop here that we're interested in, just that there has to be something that it decays into in the final state. So let me just use a capital letter psi to abbreviate the appearance and a blob diagram here to abbreviate whatever it is that appears in the final state here. Then we can calculate this loop, but we have to add to it the term with the counter term in the vertex. Okay, so I'm just applying the Feynman rules back here. And let me group this diagram and this diagram together and just call that a form factor capital F of Q squared. So if masses are small, then that's the only Lorentz invariant that form factor can depend on. So how do these notational conventions appear when I start writing down the expressions for these diagrams? We have it down here. So if I imagine I'm doing an unpolarized cross-section, so I average over spins, the spins of these quarks right here, then I get the psi just appearing inside of a trace. I should just have an overall scalar form factor out front. Okay, I've got the I lambda from this side of the cut right here. And of course, I've got the polarization wave functions for the quarks here and here. Now, if I were just calculating a diagram like this, I might treat the F as having Dirac indices, and it would appear as a form factor I'm calling here F with a bar on top of it. Okay, so if I were just following the rules for appending pieces of the Feynman rules to one another, then I would get something like this. And then to get the form factor, well, I'd say this Dirac matrix f with a bar on top of it can be expanded into form factors. If it were something like a vector coupling, like in QED, we'd have to worry about a Dirac form factor and magnetic form factor and so forth. But since we're working with the scalar theory, we just say f bar has only a scalar form factor component, and then all of the Dirac indices just have to be a unit operator. And then to pull out the scalar form factor, I just do 1/4 the trace, the Dirac trace of that f bar. Okay. So I hope that's clear. And then I also have to note that, well, if I look at this contribution, then I would just have a minus I delta lambda there. Minus I delta lambda. So let me call that contribution to f subscript ct for counter term. And so we're going to have to calculate that f subscript ct from here, and we're going to have to calculate this diagram, which I'll call the f unsubtracted because it's before we add the counter term and subtract the pole. So we want to find delta lambda, and delta lambda is only coming from the pole part, so we can get there pretty quickly if we just for now ignore all the finite contributions and look at only the poles that diverge when epsilon goes to 0. Okay, so f unsub is what I'm calling this. F unsub, and this is what I'm calling f counter term. All right, so we'll start with f unsub, and that comes from basically taking this trace of the diagram. Well, let me just copy and paste that diagram. Maybe blow it up a little bit. Okay, so the thing we need to calculate in order to get f unsub is just this triangle part right here on the inside, including the couplings at each vertex, but when we've already accounted for the wave functions outside of that triangle, so we're not going to write that down. Okay, and then we need to calculate that and then take the trace of it and divide by 4 in order to get this form factor f of q squared. So go ahead and do that and check that you get the same thing that I do. Okay, so we've got the trace of basically 2 propagator numerators here. That's what you see right here. We've got the 1/4 coming from up here. We've got 3 couplings, lambda mu to the epsilon, lambda mu to the epsilon, lambda mu to the epsilon. And those all appear right here. Okay, maybe keep track of the number of factors of I. We've got minus I, minus I, minus I, and then I for each of the propagator numerators. So that's essentially minus I to the 6, which is just a factor of 1. So it's a positive sign here. We've got the 3 propagator denominators from each of these lines. You should see here. Then we've got the integration over all of the unconstrained k, which is what I'm labeling as the unconstrained momentum running around this loop. And it's in 4 minus 2 epsilon dimensions. So if you have to review the QFT that we talked about last year, go ahead and do that here and make sure that you agree with that. Now, calculating that trace is fairly straightforward. Comes with a factor of 4, so we get rid of that 4, and we get a bunch of Lorentz invariants now in the numerator. No more Dirac indices floating around. Okay, now the next set of steps are hopefully fairly standard for you now. You can basically look in the textbook like Peskin and Schroeder, look at any of the example calculations that we did, what are done in the textbook, and look at identities in the appendices. Okay, so for example, we can combine all of those denominators using a Feynman prescription, a Feynman parameter prescription. So I take all of these denominators here, I introduce an x, y, and z, and I integrate over x, y, and z from 0 to 1. And each of these denominators can be combined and placed into one big denominator. Since there were 3 of them, now they're all raised to the power of 3. So view Feynman parameter here, Feynman parameters. Note the factor of 2 because we've got 3 denominators now here, and the delta function that sets x plus y plus z equal to 1. So the next set of steps are just simplifying that expression. All right, I would say go ahead and check that the denominator can be rewritten in this way. So den stands for denominator. I'm now simplifying the expression of the denominator such that it will be easy for me to just extract the 1 over epsilon pole out of this integration. Okay, so actually the denominator, and again, I'm kind of not caring much about masses because I know that for these ultraviolet divergence 1 over epsilon poles, they're not going to matter. So 1 over plus masses squared, I want to be pedantic. And hopefully, if you do that, hopefully if you take out a piece of paper, you can check that this is just another way of writing that previous line. And what's great about that is I can now just take this momentum in here and rename it some other momentum, some other form of momentum L. And then I can change variables for the integration. And then I get an integration just over this L squared in the denominator plus stuff that is just constant as far as I'm concerned. So in other words, something like this. Okay, where does the L squared in the numerator come from? Well, if we look back here, you'll see that it just comes from the k squared here. So once we do the change of variables, that k squared becomes a factor of L squared. The other terms here are odd and are going to give something odd in L. So they don't count. We've got a factor of 2 still sitting right there. So you've still got a factor of 2 here. And okay, we're not worrying about stuff that has masses, say in the numerator, things that aren't going to give ultraviolet divergences. We don't care about if we're getting the 1 over epsilon pole. So I'm just going to write plus finite parts. I'll be dropping anything that doesn't contribute to the 1 over epsilon poles. Here I've also taken the z integration that sets 1 equal to x plus y plus z. And that allows me, I've actually used that in several places here. Okay, so again, check that. And that allows me to reduce the expression quite a bit, the structure of it. Now note that y goes from x to 1 because that's the phase space that this delta function constrains us to. Okay, but then once I've gotten the integration over L, the 4 minus 2 epsilon dimensional integration over L reduced to this form, I've got a nice set of integration tables that tell me what that integral is. I can just defer to those and write down the integral. So for example, I think the textbook Pechkin and Schroeder has all these integrals written down in their back. And that's all I've done here is substitute in the result for that integration. I've abbreviated this combination here, 1 minus x minus y, yq squared by delta squared. Of course, it also contains masses, but again, we're going to ignore those. Of course, I haven't accounted for the finite parts, but I'm just going to remind you that they're still there. And I think now the next steps are just to simplify this expression and figure out what the 1 over epsilon pole is there. Do that on the next page. There are several things that you can do. For example, gamma of 3, that's just a factor of 2 that allows me to cancel out this factor of 2. That's nice. So what I've done up here at the top is identify the factor of S sub epsilon, because remember, if I'm doing MS bar, I wanted to remove S sub epsilon over epsilon poles. Remember what that was. S sub epsilon is equal to 4 pi to the epsilon over gamma 1 minus epsilon. So the 4 pi to the epsilon that was originally associated with this 4 pi is right down here on the previous page. So I've just taken out that 4 pi to the minus epsilon, put it in the numerator, and that becomes the 4 pi epsilon that we have here. I've multiplied by an overall gamma of 1 minus epsilon in order to have a 1 over 1 gamma 1 minus epsilon here. Okay, I've done just a few more rearrangements and check that that all works out. Continue that down to the next line, and what I get is here. Notice that I've split all the stuff associated with the lambda, because I know that in the end, the delta lambda is a correction to lambda mu to the epsilon. So I'm going to keep one factor of lambda mu to the epsilon out front, and then there's a mu squared mu to the 2 epsilon. The dimensions combine very nicely so that I just get e to the epsilon log of mu squared over delta squared. I have something that's going to give me a logarithm involving mu squared over here, but now the dimensions are transparently correct, and I have I've put the other lambda squared in here. Just a few more simplifications. Well, okay, now it's pretty easy to see what the 1 over epsilon pole is, right? So here's the S sub epsilon over epsilon. I drop anything else that involves epsilon because that gives me just a finite part. I can do this integration here because I'm not integrating anything, right? That integral is just a factor of 1/2. That's where this 1/2 comes from, plus whatever finite parts I get from, well, from what I already had, and also from multiplying 1 over epsilon poles by epsilon. Okay, so we're getting very close to the final answer. Just one more little bit of simplification. This is what I want to work with to get the lowest order beta function. So we might actually say plus stuff we drop. That's the result right here that I want. Okay, so maybe pause the recording now. Make sure that you can follow the steps that I laid out here. Okay, so we've essentially gotten this back here. Copy and paste that. Well, what we really got was pole part, or more accurately, S sub epsilon times the pole part. And then what we need to do, well, and that's the pole part of F on sub, and we need to add to that F counter term, or perhaps we should just draw it like this and get F counter term. Now, all we need to get that is to remember that there should be no pole parts left over once we add F sub counter term. So F sub counter term in the MS bar definition exactly cancels out whatever pole part that we got here. So we can see immediately what it is. Remember that F counter term from the Feynman diagram was negative I delta lambda. Important to keep track of these signs and the I's and so forth. But we know that when we add this, as we did here, it just has to cancel out that pole part. So we immediately know what that is. Delta lambda is just all of this stuff without the overall factor of I. Okay, maybe we even put a box around that. Okay, so this is the place where we now switch to getting the beta function. We've got all of the counter terms that we need, all of the delta whatevers. Okay, we got the delta z's from previous lectures and so forth, and I wrote them down on a previous slide. Now we just have to go back to the very beginning, look at the way we organize the Lagrangian back here, and figure out how to relate lambda to lambda subscript 0. That's what we really need to do. Okay, so we have here the relationship between lambda b and these things. But of course, we don't want the relationship between lambda b, lambda basic, and lambda. We want the relationship between lambda bare, the bare lambda subscript 0, and lambda subscript 0 is equal to zq 1/2 z h 1/2 and z s 1/2. If we just follow the steps going from here to here, right? We substituted in for side 0 z 1/2 subscript q times psi. We substituted for h0 z subscript h 1/2 times h, and we substituted for phi subscript 0 z subscript s 1/2 times psi. That all went right in here. And so when we had lambda subscript capital B, we actually have this times lambda 0. All right, so now we have to, this is where we have to use our results for the ZQ, ZH, and ZS. Go back to our slide where we had gotten to. So we know that what I just said is true. Lambda B is equal to all of the z's to the 1/2 times lambda 0. And we know that lambda B is equal to lambda mu to the epsilon plus delta lambda. We just said that also. And we know how to relate delta lambda just to lambda, right? Okay. So we know how to relate lambda sub 0 to lambda. And that's what we have to do now. So I'm going to substitute in, well, I'm going to move all of these factors to the other side of this equation. And I'm going to use delta lambda to write this expression. Okay, and then denominator, I've got a ZQ times ZH, and each of those is raised to the power of 1/2. But ZQ and ZH are exactly the same. If we look back to the previous slide, each one was square root of 1 minus lambda squared over 32 pi squared times the pole part. And since we've got two factors of them, I'm just going to remove the square root sign. Then we've just got z sub s, which was square root of 1 minus lambda squared over 8 pi squared. Okay, so that's all sitting in the denominator now over here. I've written it like this. Then I've got delta lambda from the previous page down here. And I'm going to pull out the factor of lambda mu to the epsilon so that I get this. And then over here, I'm just reminding us that this is not really the full relationship between lambda 0 and lambda. It's just the relationship through order lambda cubed. So there are terms that we're dropping when we manipulate this formula. We shouldn't forget that, but that's what we're going to do for now. Then it's just a matter of expanding or simplifying. You can immediately see that, well, having this in the denominator, if I'm only worried about stuff up to order lambda cubed, then I can put that in the numerator and just change the minus sign to a plus sign. Similarly, for this stuff under the square root, I can put that in the numerator if I just change the minus sign to a plus and include a 1/2 right here to account for the square root. And then everything is just, again, any errors to those manipulations are just, again, power lambda to the fourth or higher. Suppressed by lambda to the fourth or higher. And then it's just a matter of multiplying all that out. Plus dot, dot, dot. And I get the overall factor of lambda mu to the epsilon times 1 plus 5/2 times this combination of factors lambda to the squared over 16 pi squared times the pole, and then plus stuff that I'm going to end up neglecting. Okay, so this is really the result that we're looking for by calculating all of these counter terms in MS bar. And it's an equation that relates lambda sub 0 to lambda, which is now appearing here and here. And if I went to higher orders, I could calculate all of these higher order terms here, along with they'd all be coming with 1 over epsilon, higher powers of 1 over epsilon poles. Okay, but the point is that now I can use the fact that the original theory had no dependence on mu at all. It's just defined independently of the particular choice of scheme. Therefore, if I take the derivative with respect to mu, and remember, using different values of mu amounts to just using different renormalization prescriptions. And since the original lambda 0 had no renormalization prescription because we hadn't renormalized yet, then the derivative with respect to log mu should be equal to 0. The log mu is because it makes these equations come out nicely. And so all they have to do is apply that derivative to this expression. And ultimately, that's going to tell me and set that equal to 0. That gives me a constraint now when I do the derivative of all this stuff from the previous line, and I take the derivative of that with respect to log mu and set it to 0. That's going to give me a constraint on the dependence of lambda on mu. And notice that I've written lambda mu to the epsilon just as e to the epsilon log mu, because that makes taking this derivative nice. Just a notational thing. I'm going to call the derivative of lambda of mu. And remember now, since mu is changing and that's causing lambda to change, I'm going to write lambda as a function of mu. And I'm going to call that derivative beta, function beta, with a bar on top. The bar is just because I'm going to change the definition slightly by overall factors later. But okay, with that definition, now we set 0 equal to the derivative of all this stuff. So we can do the product rule, take the derivative of this first, multiply it with what we have here. And we just get epsilon lambda mu to the epsilon times all of this stuff. Okay. And then we have to do this factor, which again is just mu to the epsilon times the derivative of all this stuff. So that's mu to the epsilon. And now we use the chain rule. The derivative of lambda with respect to mu is just this beta bar I've written here. And then if we go inside here, we've got, well, this lambda squared times this lambda. We've got 3 powers of lambda. So when we do the chain rule there, we get a factor of 3, 15 over 2, lambda squared over 16 pi squared now times beta bar. And we shouldn't forget that we're dropping stuff, so plus dot dot dot. But remember, we're just working to order lambda cubed and no higher here. And then it's just a matter of solving this equation for beta bar. That's what we have here. I've just isolated beta bar on one side of this equation, moving this to the other side of that equation, and dividing everything here after factoring out the beta bar. And I get something that I can again expand in powers of lambda squared. Okay, that's fairly simple to do. Again, I just moved the denominator to the numerator and changed the plus sign to a minus sign and expand everything out. And now you see that through order lambda cubed, I don't have any 1 over epsilon poles anymore. And since that's beta bar, that's equal to derivative of lambda with respect to log mu. So if I drop these higher order contributions, I can get a good approximation to how the lambda varies with mu, the different choices of mu. Now, if we wanted to, we could keep going to higher orders in lambda. And if we did that, we would find the same thing. There would be no 1 over epsilon poles in beta bar. We could truncate at a certain order, get a very good approximation to beta bar, and solve the differential equation. So in other words, we have here, this is beta bar, and beta bar, if we truncate so that we drop anything past order lambda cubed, then beta bar of lambda is equal to 5 lambda cubed over 16 pi squared, and that's with taking epsilon to 0. All right. And we can solve that differential equation. Actually, before we do that, I'm just going to make a few more cosmetic changes. So I'm going to notice that, well, if we keep going in this direction, we get 2 factors of lambda every time we go to a higher power. So be better maybe to work with derivatives with respect to lambda squared rather than with respect to lambda. So that's what I'm going to do here. And also, those factors of lambda squared, those powers of lambda squared tend to come divided by 16 pi squared. So I'm just going to include that in what I'm differentiating here as well. Just notice that if I differentiate lambda squared over 16 pi squared, okay, then by the chain rule, I get this expression, and this is now the beta bar that we just had. Okay. And beta bar was this expression, 5 lambda cubed over 16 pi squared. So I plug that in there, the 5 becomes a 10, and I get 2 powers of lambda squared over 16 pi squared. So what I'm going to do is define a subscript lambda to be lambda squared over 16 pi squared, and beta without the bar on top of it will be the derivative of a with respect to log mu. So the derivative of this thing with respect to log mu. And the 10 is a nice round number. So beta, the final beta, is equal to 10 lambda squared plus terms that I drop if I want to go only to a lambda squared order. And this is the result, of course, when we remove the UV regulator by taking epsilon going to 0. Okay, so this is the lowest order beta function. Some things to notice. One is that it's positive. Beta is greater than 0. That means that as I raise mu, so as I incorporate higher and higher energies or smaller and smaller distances, the coupling gets larger. And so it doesn't have the asymptotic freedom property that we're often talking about when we're talking about QCD. So that's an important thing. And of course, if you start adding higher loops, you can get this beta function to as many orders as you like. Once you truncate that series expression for beta, you've got a differential equation that you can solve for a sub lambda as a function of mu, the renormalization scale. If we truncate here, just drop this term and solve that expression, then you get an approximate solution that looks something like this. Just check that when you plug that in to the definition of beta, you recover this relation, this renormalization group equation. Okay, this is equation for the running of the coupling. And here, mu0 is like a reference scale. So we basically determine what the value of the coupling is at some scale that we call mu equal to mu0. This logarithm vanishes. And once we know the coupling of that scale, we can use this expression to go to higher scales and figure out what is the coupling at the higher scales in terms of the coupling at this reference scale. It's maybe instructive to just go ahead and plot that. Here I rather arbitrarily chose mu0 to be 1 GeV. So we're living in a universe where this theory is real. We might be doing an experiment where we fix the coupling in an experiment at mu0 equal to 1 GeV. And let's say that the coupling is some generically small value, 0.001. Note that it's actually not that small, especially when you account for the fact that this is A, which already comes with 1 over 16 pi squared. So the value of lambda squared is going to be quite a bit larger than this. But okay, this is a nice round number to use for our illustration. And this is what it looks like when you plot it. And notice that the horizontal axis is logarithmic, and it goes all the way up 40-something orders of magnitude from the lowest value. And for the most part, the coupling just doesn't evolve whatsoever. Makes sense because deviations from a constant coupling are higher order in the coupling. Okay, we might zoom in on a somewhat smaller range. This is plotting this expression from, well, 1 GeV is here, and we go all the way up to 1,000,000 GeV, so 6 orders of magnitude, and you get a very, very small, slow increase in the coupling. In fact, it rises in that range by about by just over 10% from its initial value. So it's a small effect. You have to see it over many orders of magnitude if you want to be able to see it. Okay, just let's see, a few other things. Notice that eventually it blows up. This is this infamous Landau pole issue. If we go way out here, the coupling eventually blows up. If we use this expression, we can get a very, very rough idea of where the divergence in the coupling should take place by just solving for where the denominator goes to 0. If you do that, you find the coupling diverges when mu is around the input scale e to the 1 over this stuff. Okay, so if we just plug in the numbers we had before, we expect a diverging scale at around 10 to the 43 GeV. So it's an astronomically large energy scale, and that tends to be typical for these weakly coupled theories. Okay, so I hope this is a useful exercise for everybody to look through to get used to, the concept of renormalization beyond what we were able to cover in detail in our QFT class. This theory is very useful for exploring and extending the ideas of parton densities, like what I talked about in my previous few lectures for YouTube. So it's good to get familiar with it. We can use it in that context. That's probably what we'll do next. Okay, but for now, I think this is enough. Make sure that you can retrace the steps that I've made here and understand how couplings run. And with that, I think I will stop for now.